because then we can actually also start looking at the transformation, and that's when it's going to get interesting, because you want to transform your position based on what your current rotation is. So that'll get interesting in a bit. There's some math involved that I cannot remember off the top of my head. That, by the way, is a sentence you're going to hear me say a lot while we're doing this thing together, because it's been a while since I've done this kind of programming. But hey, it's fun. And it's always fun to rediscover stuff. So let's just do a little bit of simple stuff here. So if we press W, so W is moved forward. Then we want our position, our Z-axis, to be something, and I'm trying to remember exactly what. So we're going forward, that means we're going down negative Z, so we want to actually, now here this is a sort of funny thing, positions, you want to use the delta time so that the quicker sort of the updates come, the less you're going to move between each update, whereas on the mouse you don't want to add the delta time because people get twitchy and you don't want to scale with, because if you do sort of scale it, then people will move the mouse a constant amount and you're getting sort of the amount of motion they have in just one little slice of that time. So it's already sort of implicitly multiplied by delta because people have a sort of a fixed speed they move the mouse, whereas keys are either on or off. So also if you're like using a joystick, you're not going to want to use the delta. Generally for sort of like absolute positioning or more analog things where you get a value, you don't want to use the delta time, whereas if it's just Boolean 1, 2 or 1, 0 on off, you'll usually want to multiply the delta on because then it's going to be dependent on how long you press it. So like that's the way you can think of it. How far I move depends on how long I press a key, whereas how much I turn with my mouse does not depend on how long it's taken me to move the mouse. I mean, if I move my mouse from one point to another in like 10 milliseconds, or if I do it in like 10 seconds, I should move the same amount. So that's why we're multiplying delta one place and not the other. And then we're just sort of scaling it down so that we don't move insanely fast. So also if the S key is pressed, we want to move the other way. Then we have the A key and the D key. This is around the X-axis, so that should give us sort of primitive movement. So let's just take a look. Yeah, I can move! You see, this is where it gets dangerous because I could play with this all day now and we'd never get any more done. So I'm going to have to force myself to do more. And the next thing we want to do is we want to add the pointer lock so that we actually get mouse motion no matter what happens. And you can sort of see it's limited by how big my window is right now. So, pointer lock. How do we get a pointer lock? This is where we hope that Google will be helpful. Piss off, Google. There we go. So, let's see if we can find something on pointer lock. The interesting, I don't think we have pointer lock, yet we're getting those two fields. Oh well, not that I'm complaining. So I can get sort of a pointer lock event. That's the thing. Pointer lock hides the mouse cursor and exclusively gives the target element relative mouse movements. We definitely are not hiding the mouse cursor right now. So we can do this request pointer lock. So, but for web security reasons, its associated request can only be raised inside the event handler for a blah blah blah. See functions affected by web security for more information. So we probably wanted to just defer until in an event handler. And we need to know what we want to have grab the pointer lock, which is going to be our canvas object. So we're going to try and see if we can't locate that. Great, there's our input class. So what we want to do is we want to try and request description request pointer lock. So we can request a pointer lock. We need the name of our canvas object or the ID of our canvas object. So looking through this wonderful, absurdly horrible HTML. At some point we're going to rewrite this, but it works for now. There we go. Our wonderful little, somewhere there's a canvas. It's called canvas. Yeah, that'll do. So we want to establish a pointer lock on canvas, and we'd like to defer that until we're in an event handler where it can be done. So with any luck, we should actually grab a pointer lock now. So let's see how that works. Yep, I'm getting a message that I have pointer lock now, and you can't see my pointer, and yay, I could press escape to get out of it. That's always the interesting thing. How do I get out of pointer lock again? So far so good. We have callbacks, we've got pointer lock. Now what we should actually do is we should try to get sort of the proper setup for a my brain fails me for a moment. We'd like to get sort of a proper setup for our movement keys, because right now they are kind of mapped weirdly. If I've just refreshed the page here, and we just grab that pointer lock, you can see that even when I'm sort of standing side on here, I'm pressing W and S, I'm still moving in the same direction, and A and D is moving me along the same axis. What we really need is we want those keys to be relative to sort of our current direction that we're pointing. So that means that we want to actually, what we want to do is we want to use these to set up sort of a local one. Then we need to multiply a rotation matrix onto that, and then we apply that to our current position. So that's going to be fun. So that's sort of our camera logic over here. This will probably be moved to something other than a camera at some point. So what we need to do is we have I'm just thinking for a moment for some odd reason. So essentially these should not be influenced by our up-down motion, but only by our pitch, but only by our yaw. potentially by role, but we're going to ignore that for now because I really can't be bothered to take care of that right now. So what we're going to do is we are going to start a GLM 3D vector here, which is going to be our motion, which is we're just going to 0 initialize, and then we are going to update this temporary motion vector rather than our position directly. It's sort of still the same idea. Then we are going to create a nice little rotation matrix here around our y-axis, which is the one we care about. We'll probably want to do this after we've updated our y-axis for our mouse. So we start by updating based on the mouse, and then we update our local motion vector, and then we are going to set up a quick little matrix here. And it's just going to be our motion transform. Just going to 0 it or 1 initialize it, so it's identity. Then we apply our rotation around the y-axis. And then what we want to do is we want to take our current position, take our motion transform, multiply our motion onto that, and then we need to grab just the x, y, and z of that. I wonder if, yeah, I need to do a 4 vector of this for that to. Ooh, really, it doesn't. Anyways, that means it's mainly zeros with a 1 at the end. Anyways, that seems to magically work, or nope, it doesn't. Great. Then I'm a little bit more calm. So we can either do this by hand, or we can be more sneaky about it. So question is, does GLM rotate it only for 4-dimensional matrices? So what I'd like to do is essentially see if there's a way to take just the 3 first coordinates of a 4-dimensional vector, technically this is still motion. We'll take care of that in a moment. The swizzle operators. So it has functions, maybe? If you do this wonderful thing, GLM swizzle, Yeah, let's try and enable that. So before we start working with that, I'd like to define this and see what happens. So with any luck, I can then say dot x, y, z at this point. Might want to do that globally just so that they're always available. So we're going to go for the CMake file here, and so I'd like to set CMake, and that'll be CXX flags as well to define GLM swizzle, and then try and recompile. Nope, no luck with that. Swizzle plus 11. So there's an extension implementation which looks like this. Yeah, we'll give that a go. Close enough. So in our camera here, I need, and it's a somewhat stable extension to GLM. So what we want to do is we want to get cpc/wiz. I'm getting worried. I don't like the color of that. Especially because it does not exist here. GTX? Nope. So yeah, they're talking about it, but I can't, as far as I can tell, it doesn't exist here. Let's take a look here. Our alternative is to just consider position to be a 4D vector. It's doable, but I'm not sure Translate will be happy about that. It really wants a 3-dimensional vector. And in case you're wondering, this is kind of what it does. Anyways. So another possibility that we could do is we could just try and maintain a sort of constant motion transform, or a constant transform that is just where it always is, and then just sort of build on that cumulatively. It's also a possibility. And strictly speaking, it shouldn't be that difficult to do. We're gonna give that a go. Should be a little bit more effective as well. Or so we like have this. We're going to save the projection transform, but we're not really going to use it because then we're going to have a projection view transform. So this is going to be both the projection and the view transform in one. And that means that our transform function will just return that. And to set it up in the same way as before, what we want to do is we want to set our projection view transform to be a translation of this. So this way we are just going to have a static setup like that. So what we do is we do at every step, we're going to update our projection view transform by rotating it. So first we have a Y rotation. No, that won't do because we have the Y rotation and the roll, and it's going to really make stuff weird. So we want to keep it separate. There we go. Okay, so this is gonna be the really annoying way of it. So we're gonna do it this way. We're gonna say motion is then just this transform motion. And then we are going to create our own free vector here. So this consists of motion.x, motion.y, and motion.z. And that at least should work. Yeah, that header still doesn't exist. Let's see if we got this just somewhat right. So we refresh. No. So this is interesting. So let me just. There's a little bit of work needed. Okay, so I'm pressing forward, forward, forward. If I turn here, now I'm going away. So now I'm pressing backwards and I'm going towards it. If I turn, I start going away from it. And, oh dear God, this is horrible to control. So, somewhere we're doing something very, very wrong. And I'm trying to sort of, I think we might need to use sort of the opposite rotation. And technically this is sort of a motion, not a point, so that should be 0. Let's see what happens now. So yeah, we've now got the correct form of motion. So we've now got relative motion compared to our pointer, and still a lot of text output. So just for reference, what I did, I put this W component of the motion to 0, and I negated the rotation down here. And that was it. So let's just kill off some of that output for the mouse moves. And that allows us to actually move around. So that is sort of the simple stuff. What we're going to do now is that we are going to take a little 10 minutes break, and when we come back we are going to try and render an actual cube and see if we can't sort of again do a little bit of factoring so that we factor out the idea of having a cube and out of the renderer, so that it gets past some sort of list of renderable objects, and that is what it will show. But first, we're going to have a quick little break.